Okay, we're live. Hello, I'm Eric Decker. Welcome. I'll be your moderator for this event. We have a great panel to discuss schedule challenges, the trends that drive them, and the strategies to cope with them. I've led teams at Fusion.io, Samsung, and Mythic, and I'm really starting to wonder how long we can keep our head above water as an industry while we adapt to the increasing demands that we're seeing. It's hard as an industry to study these topics objectively because hard data is difficult to find. Companies aren't going to share their schedule data. They're certainly not going to publish how far behind they were from where they attempted to achieve a product or tape out. And each project is unique and hard to compare directly. So for that reason, I would like us to have a conversation today exploring the subjective experience of our panelists interactively with you, the audience. So please submit your questions to the Q&A box, and not the chat, so that they can be captured and sent to our panelists when the session is over. I will let the panelists briefly introduce themselves, starting with Mark Glasser of Cerebras Systems.
Hello, I'm Mark Glasser, and I'm a verification architect at Cerebras, and we're working on large-scale engines for the AI market.
All right, thanks, Mark. Brian Murdoch from Cruise.
Hi, I'm Brian. I'm currently doing more validation and firmware development at Cruise, but I've also done verification, and that's kind of how my career has gone, as I've bounced back and forth between verification and firmware development.
And Dan Romaine from AMD.
Hi, everybody. Dan from AMD, a verification manager there, and I've spent 20-some years in the ASIC verification industry, everything from consulting firms to product companies and even EDA, but don't hold that against me.
Thanks, Dan. And Jason Sprott from Verilab.
Hi, I'm one of the co-founders and the CTO in Verilab. My background's in ASIC, FPGA, and real-time embedded systems. Since Verilab was founded in 2000, the company and I have been focused on pretty much all forms of functional verification. I'm a verification engineer as well. I'm specifically interested in welding together the depth and the detail we see in hardware verification with the style, the scalability, and the reuse we see in software development. That's what I'm into.
Sure. Thank you. I guess to start off with, I'd like to explore the trends that we think are affecting design complexity. There's obviously, a lot of different things to choose from. It's a recurring theme at every DVCon, but maybe if we could start with you, Jason.
Trends, well, I mean, I guess that the biggest thing these days, I would say, is, well, the biggest things are the kind of heterogeneous computing environments we see on chips now. I mean, CPUs, GPUs, MPUs, embedded FPGAs, although I've not seen so many of those, but they're coming, they're there. All of these kind of things on chips, it's just massive, massive amount of stuff. Add to that all the mixed signal things we get these days from all the sensors. It's just a huge amount of complexity that drives other complexities in software and things like that as well, and the interactions between all these different blocks. I would say that they're never truly independent, even though they're individual subsystems. They're quite tightly coupled sometimes in terms of functionality and interaction. Yep.
Thanks. Dan, do you have anything you'd like to add to that? You've spent a little time in the mixed signal space and seen a few different things.
Yeah, I think huge challenge there is, two radically different disciplines. You've got the voodoo magic on the analog side, and you've got the kind of code-centric, tech-centric digital guys, and bringing those two worlds together is not easy. But more and more, there's tightly coupled loops between, analog circuitry that has some sensing and some feedback to digital control logic, and that's quite a challenge. And you've got code-centric people that can write models but don't understand the analog circuit behavior. And so finding a way to get those two disciplines together, I've seen as quite a challenge.
Sure. Yeah. Mark, do you have anything you'd like to add?
Well, I think what we're seeing nowadays is sort of a move away from the von Neumann style architecture for processors into SIMD, MIMD, and all kinds of other things with giant memories and caches and distributed processing, and as Jason mentioned, GPUs and CPUs and all sorts of things all together integrated onto either one chip or certainly one system. So everything you can think of is all together now.
All of the trends are working against us, I guess. Yeah. Brian?
Well, I think what everybody said, but I think what makes the verification challenging is a lot of this is IP that we didn't design in-house. Most of it is, and we don't know it very well. We're going off of a spec and asynchronous communication with the designers. I think, to me, that's what's making it very complex and difficult to verify.
And I think we still have quality issues with IP as well that we buy in. It's not always that it's badly written. It's just sometimes that the specification isn't in sync with what the user is after. But I mean, sometimes it is badly written as well. But I mean, it's not always that. And the other thing as well is the speed of change of things now. It's just because a lot of commercial products, the time to market is the big thing. And the problem there is that there's not really much time to optimize the architecture of the design, to simplify it, to make it, easier to build or verify, because you can't really think about it. You've just got to bolt some stuff together and get the thing going, and then, start to do things. And that skipped step of being able to simplify at the architectural level, I think, adds a massive amount of complexity at the digital design verification phase that you just don't think about, or that it's not thought about at the front end. And because of that, it gets paid forward. So I think that's a big deal.
Yeah, absolutely. Thanks.
Yeah, that's huge, because you have all these IPs that are trying to cover every possible use case, and you might get an IP from someone and they say this has been used in production for the past 5 years, but if you use it a little differently than everyone else has, you're going to quickly find those issues that Jason just mentioned.
Yeah, and they are complex IPs as well. So I mean, it's inevitable that it's not that difficult to use it slightly differently to the guy before you.
Yeah, and I feel like both in the RTL IP as well as the verification IP, you've got significant parameterization that can help you kind of tailor it for whatever that specific use case is. You've got challenges there in bringing in, what are your goals? What are your coverage goals, your metrics? And how can you bring that all together in a cohesive way for just the use case you want for a given IP? And you've got lots of those IPs.
Yeah, and I guess one of the trends now that we see as well that, I mean, it's more specialist, but security and safety features. I mean, they're just verification things to verify for us. They're not, they're just other features, but they're complex. They're things that are adding over a normal piece of design. They're adding a layer of complexity that wasn't there before, like duplication, lockstep stuff, additional features that need to detect or correct for things. And these things are kind of layers upon layers above what you had. And sometimes the kind of things that you have to verify on these things and the design that has to be done on them it comes in quite late, or it can be changed. And these kind of things are definitely adding more spice to the pie.
Definitely higher stakes on some of those if a bug does slip through.
Yeah, that's right. I mean, the high reliability things are kind of, the stakes are high. You can't just get away with saying, we'll take a respin or something like that. Oh, you can do that, but not when you're on your final product.
People do.
I mean, it's a big deal. If something gets missed there, if it's going into space or
Well,
something.
so when we talk about, a lot of these different factors, the challenges of IP, et cetera, are we just getting worse at building our schedule estimates? Like, we feel schedule pressure, but how much of that is that we have a bad schedule to begin with, and how much is that, that there are unforeseen challenges? Like, what do you think? I mean, like, I don't know too many people that tape out ahead of schedule, so I feel pretty comfortable saying that it's hard to hit schedules. So what is it about that part of the process that seems to elude us?
I think that engineers are notoriously bad at estimating schedules. I don't think this is a new thing. I think it's always been like that. They say, well, that should take a couple of weeks, and 6 weeks later, it's almost done. And the other part of it is debugging. So bugs, you can never predict how long it's going to take to find a bug. You can predict that there will be bugs, or you don't know which ones, but claiming that will take a week to fix or to find a bug, find the root cause and fix it. I don't know. It could be a day, it could be a week. You can't predict that. It's very difficult to tell.
Yeah,
I think that throws schedules into a tailspin very often.
I don't know if we're worse at doing schedules or any worse than anyone else, but
No, I don't
I
think
think I think that the thing that's changing a wee bit, or the thing that we don't take into account enough, is all the unknowns. We know they're in there, right? We know there's unknowns in there, but we don't seem to do much about that. And I think somebody needs a schedule to show that the tape out's going to be well, it's always at Christmas, isn't it? The tape out's going to be in December. And it's, it's like, here's the tape out, it's in December. And then you have to kind of engineer everything around where that tape out's got to be. And I think it's often driven by that. So it's, and then we're not great at admitting to ourselves, at least, that throwing more bodies at the problem isn't going to make it go faster. We think, oh, well, it takes like 500 man hours to do this. So like, we'll get 500 guys and it'll take an hour. It's like, it doesn't work like that. So, I think we don't take these things into account enough. And the dependencies, the interdependencies are huge now with hardware and software. The code development that goes on there. So it's not just our schedule, it's the impact that we have for everything else, like the bugs that's going to be found in the IPs, the bugs that's going to be found in the VIPs, the hardware, software, code development, everything combined together. We just kind of sort of don't ignore it, but
So Jason, what sort of unknowns are you referring to? Like corner cases, that sort of thing?
Yeah, I think there are, when you bolt together a whole bunch of complex IPs, that there's going to be sort of leaky seams effectively between them. There's things that, even though they're proven bits of IP, you're going to get bits of things that are going to be wrong on the margins, and you're going to get software that hasn't been developed yet, and all this. These are all things that are going to happen, and we know from history that that there's going to be bugs there. There are pieces of the spec that aren't written yet, or haven't been taken into account. So we're going to get the debug that you were talking about there, unknown debug times. We're going to get a few massive bugs that's going to take a week to debug, that kind of thing. We know that.
Yeah, when you're connecting IPs together, you have new behaviors, right? So even if a particular IP, each of the IPs have been verified reasonably well, when you connect them together, you have new behaviors, emergent behaviors, right, that didn't exist before, and now you have to figure out what those are and make sure those get verified. And I think that's part of the problem, is getting the system to hang together and make sure that all the IPs do their job in the presence of all the other IPs.
Yeah, I think we sometimes approach scheduling like a constraints theory problem, the theory of constraints, where we're looking for bottlenecks and things like that. Yeah, that's okay if you know what all the parameters are. but we haven't, we don't identify the parameters properly, and then something pops up and it's a surprise. It's like, surprise, it's going to take like a month longer than you thought. It's like, well, you should have known that because it did that last time. But yeah, it's the way it goes. But I think one of the problems with building schedules and building plans like that, let's call them plans in general, of like not just the verification, just the design itself and the verification, is that we don't keep very detailed data in a way that can be analyzed as time goes on, or normally people don't. I know some people who do keep that data, very, very rigorous data that they do make use of, especially on the back end side. But certainly on our front end side, I don't often see the level of detail that's required being recorded in order to get accurate planning on the next project, which is a bit unfortunate, because if there's one thing you have, it's the stuff that happened. You can observe it. So, if you had noted it down, that would have been really useful.
So
it's nobody's job.
Yeah, that's a good point. I was thinking, during my introduction, that it was the fact that we don't share objective data, but we don't even collect it necessarily in our own house, is kind of what you're saying.
Yeah, I think predominantly that's the case. It's not, there's some people who are really good at that stuff, but I think in general, it's just, it's one of these things that, the program manager is going to do that, or the project leader is going to do that. It's an Uber job, that's bigger than just the project manager or the project leader. And it covers quite a lot of different areas as well. It's a discipline in and of itself.
Right. Yeah, absolutely. So when I wind up looking at a lot of the solutions that are being proposed by media companies, the industry in general, I think that they fall into one of two categories for me. There's the time from when a bug is introduced or a defect exists to the time that you detect that there's a problem. And so that has to do with, things like coverage, et cetera, being able to find that part of the solution space. And then there's this period of time from the detection of the bug to when you know what the root cause is, where it goes from just being some random UVM error, well, the scoreboard didn't match, to when you're, oh, okay, I see what's happening. We're dropping something or we're doing this. Which one is the industry paying more attention to, in your opinion, or which one are you more interested? I'll start with you, Dan, on this one.
Yeah, talking about EDA and their interests is a bit tricky. The way decision making is done has shifted here and there, and each company has their own take on it. But simulation is a commodity, and so the question is, where are they really looking to get bang for their buck? And just like us in the product companies, we're looking at where we can spend the least amount of resources for the most kind of benefit, at least at a corporate level. So for EDA, I worry that it's difficult to find global solutions when companies are all finding point solutions. In the Q&A, a lot of questions are coming up, for instance, about code generation and writing in Python or some other language. And, we've been doing that for years and years as a way to, speed up and decrease schedule, correct by construction kind of coding. Which I think has become pretty popular. But the EDA is typically not heavily invested in those kinds of flows.
I think there's a lot to be said for programmer productivity. So we don't talk a lot about that in verification, but that's what we do all day, is we write code. So we need to find ways to make that more productive. Perhaps Python is one way to do that. I know that's becoming trendy right now, is connecting Python interpreters to Verilog simulators and being able to build tests that way. And I think that's very interesting, very exciting. But the purpose of that is programmer productivity, and being able to get more testing done in the least amount of time. And I don't know if Python's the ultimate answer or not, but I think that's something that we should explore more, looking at ways to make things more debuggable. being able to interrogate what's going on inside the design easily and figure out, what's happening. I think a lot of debugging time is spent on just simply trying to trace from here to there what exactly is happening. And so tooling to make that easier, I think, would be very well received, to make us all more productive and to get from here to there faster.
Yeah, I think sometimes we ask for the wrong things. I mean, to be fair to the EDA guys, we're saying, can you give us a feature to show the waves this way or put some things that way? But we forget that we've made the design badly in the first place. So the first area of productivity might be to improve the design entry in the first place, improve the quality of that, make sure there's less likelihood of the common or garden bugs going in there in the first place, and have some consistency and improvement there. That's still quite poor, I would say. I mean, in general. But I totally agree with the engineer productivity side. I mean, there's obviously ways you can automate these things, but one of the ways to improve productivity is to do things in more standard community style ways that the rest of we're writing large scale software applications, hundreds of thousands of lines of code, that are quite complex, interacting concurrent systems. It's not trivial stuff. So, other people do that as well in the software world. So, we should maybe try but they also make mistakes as well, I guess. But I mean, it's like we should try and cherry pick the areas of improvement and those sort of seams of gold in there. But I'm not just talking about IDEs and things like that to make you type in neater code or type in faster. They have value as well, but real sort of debug potential that you don't have to jump through hoops to do. Because just to get some introspection into a design, sometimes you have to spend, a day writing a piece of code to allow you to introspect into a piece of design you need to debug something. That's a nonsense.
Yeah, I think one of the reasons that Python is really popular for this is because it presents a model that's kind of abstracted away from thinking about the instructions and memories. It's more thinking about lists and other kinds of abstractions, and you can work at a bit higher level and manipulate things a lot easier than you can in System Verilog. System Verilog is a fairly clunky language. I think if we want to stay in that domain as an industry, we should probably invest some time and energy into improving that language. And I mean, all of us probably have our long laundry list of features and improvements that we'd like to see. I think collectively putting more energy into that would be worthwhile, as well as looking at other kinds of abstractions like Python or something else. One of the issues with Python, though, is it doesn't really have the hardware abstraction, right? So System Verilog is really nice that you can deal with bit strings and memories and all the timing and so forth, and all the things that we think about in an RTL design that doesn't exist, that we have to kind of either fake those or abstract, or abstract is not the right word, extract services from the Verilog simulator underlying the tests to make that work. So if we're going to move into another language, we need to think about what the features are that we need to have to make that work. It's probably not System Verilog as it exists right now.
And I think it can be quite difficult that as well, because I mean, one of the things that I mean, you can say what you like about how we do things in hardware verification, but we're pretty rigorous at randomizing and looking at coverage and things like that. Yeah. These aren't things that are done very well in the software industry, sometimes for good reasons, but sometimes because they're not very good at it and we're better at that. So we've built things in there that are actually valuable, things that have value. And, we need to keep some of those things, but unfortunately they're kludges on top of everything else. They're not like a bolt-in library, include a SciWorks library or something like that. It's not like that. It's a language extension that isn't even a domain-specific proper extension. It's like bolted into the language. So I think that makes us a bit more cumbersome to handle these type of environments and to build frameworks around that can handle these things that other people can bolt in. It's a big challenge. You need sort of IEEE standards and things like that to handle all of that stuff.
Well, let's not go there. Let's not go there.
Well, that's where we are. That's the thing.
No.
That's why we have that. You know, we have a bunch of things that allow interoperability with the languages that we use, and maybe that was certainly an approach that had to be taken at the time, but maybe it's not the right approach going forward. It's certainly you wouldn't see that in Python, I don't think, in the same way, for example.
No, I think that's an area where we could learn a lot from the software world. Having bounced back and forth throughout my career, we sure have a lot of barriers in place in our world around just collaborating on things like that. Software gets by on de facto standards because everything is open source, and a lot of things don't have to sit in committees and go through a standards process. They use a strong copyleft license on the code so that everybody can contribute and not feel like somebody's freeloading or stealing. And they operate mainly on, you know, this works and we're all using the same exact implementation of this. And so we don't need an actual standards body and paying big fees to have input into what goes into the language. And I think that's something we could benefit from here in the chip design world.
Yeah. So let me ask you this: if that were in fact the case, would you or someone from your company have the time and energy to contribute to such a thing?
As of today, no, but it's definitely a shift that would have to come, right?
Yeah.
And it didn't happen like that in the software world, right? Like it started with, you know, universities and hobbyists, but and then people within companies were started to use these open source tools, and then they had to kind of lobby their managers to be like, hey, there's this thing called open source, can I contribute to it? You know, and it grew from there. I think maybe we could skip the years and years it took for software to get there, because we can point to software and say, hey, look, this works. Every EDA company uses open source software to develop their EDA tools. And we all use, you know, as we're doing these SOCs, we all use Linux, we use GCC, you know, so it's already a part of what we do. I think just in our niche, we're not used to that yet.
Well, if you look at GCC, that's one of my favorite examples of a very successful open source project. If you have some issue with something, you have a question, I don't know, something isn't working right, you can probably post it on a forum somewhere, or just Google it maybe in Stack Exchange or something, and you'll find the answer in a few minutes, right? Yeah. We would need something like that in the in the hardware world, right? Something in DV that would be similarly effective.
Yeah, I mean, I think right now, like, we don't even know if we're allowed to talk about, you know, like if I have a problem with, you know, Cadence or Mentor's simulator, am I allowed to post on a forum? Like, what license to sign up for, and can I even say anything on the public internet? Like,
yeah, I don't know, probably not. But my point is, so my point is that do we have a critical mass? Do we have enough people in the industry that we could launch something like that, and there would be enough people to answer questions and contribute and so forth to keep the thing moving, so that it could take a trajectory like GCC, where it started from, you know, a pretty basic compiler, and now it's a very sophisticated tool, and it's very well honed, and, you know, it's reasonably bug free and so forth. It's a very reliable piece of software. Could we do something like, do we have the critical mass in the industry to do that for our tools?
I think we do.
I guess my question is, like, you know, we're talking about really complicated things like compilers, and we're talking about, you know, all this, but we're not sharing the simple stuff. Like, there's, like, you know, on the level of make, right? Like every company I know has its own roll your own solution for, like, building the design or stitching components together. Like, how many different scripts does the industry need to wire modules together?
Yeah,
One for every design.
I mean, it's true. I mean, there's all the IP exact stuff and all that doesn't solve really any. Well, I shouldn't say that. It's part of a solution, but I mean, you're looking to do something like, I mean, one of my guys today, I said, why don't we have like pip install, foo for like the chip, pip install USB, that kind of thing, and there's no real reason for it technically. There isn't. I mean, it's possible. It's just that we haven't got the amount of developers that the software industry has banging away on that problem. There's not. I mean,
we don't have the same amount, but we have lots of people banging on that problem, but nobody shares.
Independently, yeah, that's true. That is true. I mean, RISC-V is an example of that, right? So that RISC-V, you see, it's got like a lot of momentum behind it, but when you look, it hasn't got. It's got a lot of people who are interested in it, and there's momentum behind it now, but it got started with a smaller amount of people, so I think that it's like you can gather momentum as time goes on, but it's really getting something started.
Yeah,
right. And the money that the companies would spend on IP, they instead are spending on engineers contributing to that project, right? So from a resource point of view, it's neutral. From a resource expenditure point of view, it's neutral, or generally so. But the difference is we're contributing, or somebody's contributing to open source project as opposed to spending money on buying IP and assuming that someone else will support it, right? So I think that's a new model, and it's a very I think it's a very promising one.
So I'll follow up on that. Had a question from the audience. If anybody's ever tried to discuss the topic of contributing to open source with decision makers, I have been around that process before. I've never attempted it myself. What about that? How about making the case? I mean, like, yeah, we can point to software, but there's a lot of software out there that's not being made publicly available either.
Yeah, that's a tough one. I think that's why software probably got started, with hobbyists and universities, because corporations definitely have this ingrained culture of we've got to keep everything secret by default. That's our competitive advantage.
And it actually might be, if you've got a massively efficient build environment or something that like scrubs data in such a way you can discern, how bugs are correlated.
Nobody has done that in a way that is like 10 times better than anyone else.
That's true. Otherwise, you would notice, because they'd be churning out the chips without bugs and a lot faster than anyone else.
Yeah.
So to answer the question, though, yes, I have talked to managers and higher management about open source. A zillion years ago, we had a C++ verification thingy out in the world called Test Builder, and that was open source. UVM is open source, right? That didn't just happen automatically. There was a lot of arm wrestling to make that become a reality. And I would argue that UVM is successful for a couple of reasons. One is because all of the main simulator vendors have adopted it, so that's very attractive right there. Another reason is it's just everybody can contribute to it. Now there's some flaws in that, because it's kind of been controlled by Accelera, and we probably need to think about the model that Accelera uses for maintaining that, and making it more so that can be more people can contribute to that as well. And I think that's something that we need to talk about and think about further.
Yeah, and kind of going to that original question, I think, I've worked at large companies where the answer is heck no, you cannot contribute. But the smaller the company, the easier that can be. And I've had some successful discussions there where, GitHub code is involved, right? And in some of these more simple things where, you're not talking about trade secrets, but little bits that when put together make a good flow.
Well, I think one of the things that companies need to think about, and many are, is open source as a business model, right? So RISC-V is an example, right? So that's open source, but people are using that and building businesses that are profitable. And I think in like the world of UVM, EDA companies are using UVM to build other kinds of tools around that that are interesting, generators and visualizers and debuggers and whatever, that are profitable, right? Based around this open source tool. And I think that open source as a business model is something that is being used effectively and can probably be used more effectively in our industry.
My hope is, attending these conferences over the last roughly 20 years, it used to be, everyone here worked for, Intel, HP, IBM, and now you see software companies here, Google, Microsoft, Apple, and these companies have experience with that open source business model. And so my hope is that's going to help us get there. I think, if you're still working for a stodgy old hardware company, you might have a hard time getting permission to contribute to open source. But if you work for a company that does a lot of software too, maybe your immediate managers who are sort of steeped in the EDA tradition, they might not understand what you're trying to say, but if you can get in touch with people on the software side, maybe there's a hope there.
Well, you see it happening now with the Chips Alliance type thing, where Google's involved in that, and other companies like Antmicro and stuff like that there, and stuff's actually happening. Development's happening. I mean, it's a real challenge to produce something as stable and comprehensive and high performing as an industry simulator. That'd take a long time to develop that, but there's other things that can be developed, or you can develop something that's fit for purpose that many other people would want to use as well, that wouldn't be buying these simulators anyway. So, if you're making more of a community, making it open to people who wouldn't normally be part of the customer base and things like that. So the Chips Alliance stuff is quite interesting in that respect, just looking at what's happening there. That was a lot going on. You can see tons of work happening under the surface, but you're just wondering what's going to pop out of that. It's interesting.
Right. So another thing that I've heard from my contacts in the EDA world and so forth is that they keep coming out with new features like transaction-based verification and interactive simulation and co-simulation and all of these different visualization tools, and yet the decision makers that are talking to them are only concerned about whether they can get another 5 or 10% performance on existing techniques. And meanwhile, there's a large number of us here in the industry, and I'm not exempting myself from this, that are using, glorified display statements, UVM infos, like that's our primary thing. Let me explain some more stuff. And we were talking about like our software counterparts and some things maybe they haven't learned from us, but it feels like that's something we haven't learned from them, is like, hey, let's set a breakpoint and look at all my variables and not figure out how to pretty print them into a log and then grep them out of the log. Like, what is it about? I mean, it feels like the ADA companies are, especially the simulator guys, are giving us a bunch of tools and we're just not choosing to use them. And I'm wondering what you guys think is behind that, or maybe you've tried them and they're not any good, or it seems hard.
Well, I hate to break it to you, but in the software world, printf is still probably the most used debugger also.
Is that how you do your Python?
Actually, yeah, a lot of it. There is a pretty nice Python debugger. It's all command line. But I think those are all very specialized tools, and so like if you learn Cadence's tool and then you switch jobs and you're at a VCS house, what do you do with all that knowledge?
The transaction recording is an example of that, though. That isn't specialized. It's part of, that's available to anyone, any simulator in the UVM, and yet it's underutilized. Why is that? It has useful information. It's useful content. It's like we're not tuned in to doing these things in that way. Like there's no real portable, there are some, but it's not the portable data formats for getting in and out all like UVM portable data formats and these type of things that could be used in any tool in any way, and all of this kind of stuff to get data in and out, and that type of thing's pretty immature. But even the simple things like transaction recording, which is quite simple to turn on, people don't turn it on. Why not? Not sure. Education maybe, or actually that's a point, because there's two things that drive that. So one of them is that we run huge ass regressions and they're all offline, batch jobs, gazillions of them. And then you have to debug it at the end of the day. And that's in a different environment. You've not got the print statements in that because the log files would be too big. So you've got to reproduce it, restart from checkpoints and all this nonsense. So that affects things. And the other one is a lot of the guys are pretty junior and they don't know about any of this stuff. That's like old guys like me are getting older, and then there's not that many folk coming out with EE stuffs out and knowledge out of university, backfilling all these design verification positions with the knowledge that they need to use that kind of thing. But what they do know how to do is a UVM info or a printf or something like that. So that could affect things as well. It could just be that there's no good educational system for these debug type features that keep getting released and are actually quite useful. Maybe.
I think it is just education. People just don't know.
It comes back to the schedule discussion we had earlier.
Yep. No, that's a really good point, is that, how much of our time as a function within R&D is spent on product versus process. And the way that I've heard it described before, a common analogy is, are you going to spend your time chopping down trees or sharpening your axe? How much axe sharpening are we doing?
I'm not sure what you mean exactly.
Well, in other words, somebody can spend their time learning a new technique, examining a new process, whether it's learning formal or adopting, different tools and techniques, or you can write the agent that your boss asked you for. And how do we as managers carve out enough time for people to advance the state of the art within our companies? And how do we as individual contributors convince management to give us the time to do that?
Yeah, that's a tricky one, because it does actually cost a few projects to do that. So if you invest a bit of time into something, your project that takes the hit on that, that doesn't get that back. It's a few projects down the line that get that. And also you've got to have a wee bit of change in your pocket to be able to do that kind of thing. Big companies can maybe invest in, methodology investment and things like that. But agile startups, not so much. They're interested in getting the product out, getting the rapid prototype out, things like this. They're not going to bother about they're not taping out a test bench or a process. Whereas big companies are and should be. But then the challenge they've got after that is then the process seems to move on. You've got to be able to maintain these processes in an agile way, such that when things get better and they improve, and they have been over the past 20 years, if you think back, every single year something new's happening in verification. It's not a stagnant area. Sometimes feels like that, but it's not. There's new stuff all the time. So somebody's process can't have been the 10 years ago process. That's out of date now. It has to be the process that started 10 years ago, and now they've managed to maintain it every year, so it's kept in sync with the latest developments and the best practices that people are or that they want to use to tape out their chips effectively.
Mm-hmm. Yeah, I think it's one of the things that I've seen within companies that I may or may not have worked for is that they'll be gung-ho enough for an evaluation, and you can put the time and effort into that, say, hey, you know what, this would really benefit us. And then it's like, but there's no budget for widespread adoption. Like, there's enough of a commitment to explore new stuff, but then when it comes to not only the costs of licensing, but also, as we were alluding to a little bit earlier, the training that's going to have to take place, and not so much, you know, it's the opportunity cost of, okay, well, we can train everybody on this new tool, or we can just use the ones we've got and just tape out again, just like Rev 9. Now we'll do Rev 10 with the same techniques. And that's why I think we still see people in the industry who are running, you know, OVM test benches, and how long has UVM been around, and how many people are running on 1.1 or 1.2. Like, you know, that technical debt just keeps getting built up, because the incremental cost from one tape out to the next is not necessarily that painful, but cumulatively, I think it's been putting us in a hole, and I'm not sure how to get out of it.
Well, it's not only just cost, right? It's also value, right? So I think if it were just a matter of, like, if you bought this new tool and you could lock 10% off your tape out schedule, I think everyone would just go buy it, right? Yeah, give me a handful of those. But it's not that simple. It's not that straightforward. So the value proposition has to be very clear as to, well, if I'm going to buy this tool and spend the time integrating it into my flow and training the team on it and so forth, what do I get out of it? So there has to be some very concrete value, and, you know, usually that's measured somehow in productivity, in terms of getting things done either more quickly or with a better quality of result. Right. So if you can make a value proposition in terms of those things, I think then the tool is a big win. But some tools, I don't know that their value proposition is that clear. Or if it is just a matter of a tool, I think it's a lot of these other things that we've been talking about, like better productivity, you know, programmer productivity within the languages and systems that we use, and the whole field of using open source tools and being able to contribute to those and build those up over time and have those solve some of the problems that we're looking at. So it's not just plopping a new tool into the flow.
Yep.
Yeah, I'll come back to also, if we could somehow get everybody using the same implementation of various tools, that helps. You know, when I've hopped jobs with my firmware hat on, I haven't had to learn a whole lot of new things at each new job, as far as, like, you know, we're all using Make and GCC and the same, you know, GDB for debugging, and so I get to take my skills with me. Every new chip project I've done, it's been a different simulator, a different, you know, different waveform viewer, whatever it was the company bought before I got there. And so it's
I think that's important.
The speed curve.
Yeah, I think you've hit on something important there. The portability of the skills, how interested people are in learning them is kind of, I mean, people are wanting something that they can take to another company and it's got value. And it's weird because we see things like in companies that build chips as well, like Intel, for example, there's like DPC++ and one API, which are layers on top of GPU stuff. And that's been developed, and it's valuable to everyone outside, anyone outside Intel, and other companies who build GPUs and have these layers and all that as well. Anyone who learns how to use that layer and learns how to do that kind of stuff can do it on similar type products. So that has value if you learn it, and it's valuable for Intel, obviously, as well. But it's also value to the people, you know, upstream as well. You know, the guys who are, you know, we're doing the SQL-based stuff, and, you know, they're programming the GPUs, writing drivers for these things. All of these guys see value in that particular thing, which is why it seems to catch on. You know, but if it just benefits one guy and one company, you know, you're like, no, I really.
Yep. I know we had one, there was was a question in the Q&A about the Q&A. And I've been attempting to work the themes that I see out of the corner of my eye into this. The Q&A will be captured, and so there will be opportunities to try and answer some of these. I am attempting to go through those as best I can without disrupting my ability to keep track of everything. So thank you for your questions. If we don't get to them, it is not personal. There was one in particular that I did want to get to, that because it is a recurring theme. It was a theme in a main theme in our keynote yesterday, is artificial intelligence and machine learning. Like, is this a pie in the sky thing? Is it just exciting because everybody wants AI attached to whatever it is that they're doing now? Or is this really something that can get us to that level of additional abstraction that we were expressing interest in wanting to have in the earlier part of the conversation?
Well, one of the things about AI is it's inherently probabilistic, right? So you show a trained network a picture of a cat, and it will tell you it's 92% probability that's a cat. And so for verification, that doesn't work, right? We can't say it's 92% likely that this design will work. So we need to find a way to use those kind of tools in a way that probability will make sense. Yesterday afternoon, there was a session of several papers that were presented on stimulus generation using AI techniques that were in fact probabilistic, and being able to modify constraints and be able to change values within by looking at the result and figuring out if we're getting enough coverage or not, and tweaking constraints based on the AI engine. And I think that's very promising. I think there's a lot of neat things in there, and I hope that takes off in a big way.
Yeah, I think the productivity side of the AI, the stuff you've just described, and also poking into dark corners that you might not necessarily think to poke into, that's all. I would say that falls on the interesting side of things rather than exciting. I think then exciting stuff is probably going to come out of using these technologies over a period of time, because now we're starting to collect data. We're becoming data scientists. We're starting to collect all these statistics about things that we do, bugs in the design, all of these areas that we're poking into, the different kind of constraints that we have to use. And in addition to that, we're also, or should be, maybe looking even further downstream and saying, well, actually, when I twiddle this piece of code, this other thing always happens over here. So is that code a hotspot that needs to be heavily reviewed, or somehow attention given to, something that you knew about it before that you didn't know? And I think because we're collecting all of this data, or we're starting to collect all this data to use on things like, productivity-based enhancements, something else is going to pop out of that. Once we've got all this data, somebody's going to find another use for it that's going to tell us, that's going to give us something else, just more than just productivity. It'll give us something a bit more creative, I guess. So yeah, I think that's the exciting aspect of it is the fact that we're starting to take notice of the data now. It's maybe a bit speculative thing to say, but I think it's happened in other places. This is what's happened in other industries. That's not a pie in the sky statement. That's what's happened in other places. So why wouldn't it happen to us?
So you're saying we have this big pile of data we've been collecting, and now if we can analyze it, we can do something useful with it?
Not like you just get like a giant bin full of data and somebody's job is to wade in it. No, I think what will happen is incrementally people will start to notice things that they wish they had taken notice of, taken care to observe. So we're going to periodically look at these things and say, oh, I should have observed that. Why wasn't I looking at the Git check-ins? Why wasn't I looking at the check-in comments? Why wasn't I looking at the time to fix the bug? These kind of things. And incrementally, we're going to start looking at these things, and other interesting analysis can be done out of that may not be anything to do with finding bugs or debugging. It might be something to do with avoiding these bugs completely, or something else. So that's an exciting area. And that wasn't there when we weren't collecting the data. That wasn't even possible. But the more data we collect and the more competent we become at collecting data, because at the minute we're novices at collecting data, we're just gathering any old thing. The more competent we become in that area, then the more possibilities there are. Maybe. So I think so anyway. That's speculative, but not sort of some sort of moonshot.
Right. Yeah. Absolutely. There was another question that that had to do with formal verification and where its place in the world is. I know that this is an area that I've seen employed in the past. In the panel this morning, somebody described it as a thing that you get a PhD and then they go off and for a couple of years. And so, formal verification kind of is a big sack now. At least that's the way it looks to me. Like, there's a whole bunch of different pretty orthogonal techniques that all land in this bucket called formal. And I wonder if any of the panelists, I don't know myself, if any of the panelists here have had experience, with any of the forms of formal verification and how that's impacted things. Did it accelerate things? Was it helpful? Or maybe it just doesn't have enough penetration?
Well, my observation is that if you can verify a device formally, that's a big win, right? So that's you can just set that aside and say, okay, that's done, and that's great. It's not trivial to do that. You have to set things up, and there's a lot of work to get to the point where you can say that. The other issue is scalability, right? So there's that at some point the combinatorial explosion gets out of hand, and you just don't have enough compute resource to do the job. So that means only so much stuff can be verified formally. If someone conquers that problem, I don't know the state of the art there, but if that problem can be conquered, then it becomes more widely applicable. But I suspect that's a ways off, and so that means we're left to doing at best block level verification at the formal level, and system level verification will still be using simulators.
Does that, and you think that sort of negates the value of formal verification just because it can only do these things at
No, I don't. No, that's not my point. I'm just saying it has its limits, that's all.
Yeah, I think those limits are I also don't know how long these limits will go, but I should say, I love the idea of formal verification. I've obviously tried to use it, but I find exhaustive verification using formal properties verification, I think that's difficult. However, bug finding with formal verification, just using it as a bug finding tool and an exploration tool in that respect, I think that's got power. I think if it was branded as that in the first place, we probably wouldn't be having this conversation. It would just be another kind of bug exploration tool, and people would have learned system verilog assertions in order to do that, but like a scripting language, they would have just done it. But because we've kind of been sold this kind of exhaustive verification capability, which is obviously true, but capacity limited, then it's less attractive because it never lives up to that, as a tool. But also, I think from the formal verification point of view, the big value I would say that we should be paying attention to is the possibility for real front end, like design entry, RTL level entry, small bits of verification added in there, not trying to write properties for the whole piece of RTL you're authoring, but write properties for small bits of it. Those things live on. You stick them in there or make them available, and then they're available to the guy that's integrating the block on an assumed guarantee basis. And they still find bugs, they find bugs and changes. I think that has value. I don't know what to place on it, but it feels like it's not that, it shouldn't be that much effort in order to do that at the real design entry side. But the problem is that as soon as someone looks to be using formal, their boss or someone is going to come along and say, oh, brilliant, it's going to exhaustively verify the RTL. That's amazing. No need for all those man weeks simulation now, isn't it? And that's a big put off for people because it's just not easy to do that.
Great, thank you very much. That's our time. I want to thank our panelists for taking the time today to share their thoughts and experiences. And we'll have a look at the Q&A. If we did not get to your question, I apologize. But we will have that, and this recording will be made available as well. And you'll enjoy the rest of the conference, and that will do it for us.
Are we going to wander along to the mystical gather town
We can try
to get beaten up with swords and clubs by the audience virtually?
I'll go over to the Red Lounge or whatever I don't know. I'll wander around and maybe you'll see me.
Yeah, I'll maybe change my name on the avatar just in case. I'll wait to see if Mark gets beaten up and then maybe turn it back. Okay.
All right, thank you.
Thank you.
Thank you, guys.